Morning, everyone. So yesterday we had a look at Ka calculations. We saw that the question became a whole lot harder. In part one of this chapter, we had dealt with strong acids. They ionized 100%. You didn't need any ice table work here. But looking at weak acids here, because so little actually dissociates over, we saw how we can actually apply ice tables, use the Ka values on the data booklet to actually calculate how much H plus there is. It was a lot more work to actually get to the H plus, but once you had the H plus, it was back to the same conversions. You would know how to re-express it in hydroxide, the pH, and pOH. We'll get a little bit more practice with that in this lesson here. We're basically mirroring that lesson, but more so on the base side this time. So let's just do this by way of an example here. This first question, I still remember back in the day when there was a Chemistry 12 provincial. This is actually the question that I got wrong. Still sort of begrudging this here, but let's just try it out. They ask us here, let's see if you can find the pH of a 0.50 molar NH3 solution. Okay, so a couple things to be careful of. They are asking you for the final answer in pH. That does not suddenly make us an acid. pH is just the name of the ruler. Wherever I land on that ruler at 25 degrees, 7 is the dividing line. I just want to figure out where on this meter am I located. What will decide whether acid or base is when you're given a chemical like this, ask yourself, what is this? Okay, is it an acid? Is it a base? Is it a salt? This one here is a base. Once you identify this as a base, ask yourself whether it's strong or weak. Pretty much in part 2 of this chapter here, most of the things are going to be weak, and you can actually find this on the table. Wait a second, I thought I see NH3 actually in the strong base section. You have to be really careful. The acids are on the left side, the bases on the right-hand side. You're right. In the strong base section, so the lowest on the right-hand corner, it's actually NH2 minus on the base side that picks up the proton one-way arrows and forms NH3. I would just refer to NH3. This is actually the conjugate acid of a strong base. NH3 by itself on the base side is actually on the base, it's on the right-hand side. So when picking up proton, it's definitely more so in the weak category here. We're going to see one little side note in this section here. Unfortunately, on our data booklet, they don't give us a whole table full of Kb values. They actually list for me just Kas. If I just quote that value while we have it here, the value for Ka is actually 5.6 times 10 to the negative 10. That doesn't tell me the Kb that I'm looking for. That actually tells me how good my conjugate acid is in coming forwards. The reason why they can sort of get away with not listing for you Kb values, we learned a relationship previous. The Kw is actually equal to Ka times Kb, as long as you remember these are comparing conjugates of each other. So in this case here, if you want to know the Kb of NH3, let me just calculate this here. The Kb for NH3 is actually given by Kw, which we know, 1 times 10 to the negative 14, but it's divided by Ka of my partner. It's pretty much the reaction that I want to undo. So that is one extra step we have to do on the base side, because we're not given the base dissociation constant. I need to do this extra step here. 1 times 10 to the negative 14, divide the number on your data booklet, 5.6 times 10 to the negative 10. If I know how good this one here is an acid, I just undo that to figure out how good we are actually as a base. So this one here, 1.8 times 10 to the negative 5. Again, no units. This number pretty much doesn't change unless your temperature is different. We're at room temperature at 25 degrees. Okay, so we're ready to set up an ice table here. Being a weak base, we're looking on the right-hand side of the table. Again, unfortunately, the table has all our equations in the simple form, although instead of reading right to left, I'm just going to rewrite it left to right. So as a bronze tellurium base, the NH3 is supposed to accept a proton. It's weak, so it's going to be in equilibrium, and this is going to end up forming you NH4 plus. Before ready to do an ice table, it's super important on the base side that you write out the complex equation. On the acid side, you can still sort of get away with, yeah, pretty much we can see H+, yeah, big deal, write it as hydronium. In this case, what it's saying is, yes, ammonia is going to steal a proton, but who does it steal a proton from? Writing it to the complex equation, remember on the base side, it's sort of like adding hydroxide to both sides. And therefore, what we're actually able to track when I write the complex form, NH3 actually steals a proton from water. It still ends up forming its conjugate acid, and then it's actually the water that actually leaves behind hydroxide. Instead of worrying about, oh, a loss of H plus is making more acidic, we actually can show it as a gain of hydroxide, so that when we do actually an ice table here, we can actually track the OH minus content. So let's keep working our way through here. We had decided it was a weak base. We found it on the table. We calculated the Kb value. The concentration that they started off giving me is 0.50. So that's going to be on the initial row. Just remember for this initial row here, this one here is before any ionization. So imagine just starting off, you just produced 0.50 molar ammonia. It's all on this side right now. We actually have no ammonium and no hydroxide. Over time, it's going to follow the mole ratio. Yeah, I know the Kb constant is heavily reactants favored, but some of this is actually going to chip over and actually become NH4 plus and OH minus. I'm not actually given any information on the bottom. So what we would do here, this one here is going to drop by x, this two are going to gain by x. Remember the change line has to follow the mole ratio. This one here depends on your equation. And then anytime you have the first two lines, you can just do the math. What's 0 plus x? Well, x. 0 plus x? Well, x. 0.5 minus x. Okay, 0.5 minus x. Right? We saw because the Kb constants that we're looking at, everything on the table here, they're in the 10 to the negative something. Because the KEQ is actually tiny, it means the reactants are favored. It means, although yes, some of it actually breaks off, so little is actually going to break off. In this whole chapter, we're allowed to make this assumption, albeit you have to write this assumption. Let's assume 0.50 minus x is basically 0.5. In some sense, I'm saying the x is so minor, the x is so tiny, that pretty much so little chips off for practically 0.50. Note, we are still trying to calculate what this tiny amount is, because that tiny amount will tell me what's the equilibrium concentration of hydroxide, and that will eventually help you find the pH. But let's just keep going here. We're ready to write out the Kb expression. The Kb is products over reactants, so ammonium times by hydroxide all over ammonia. The Kb constant that we had calculated from earlier, the 1.8 times 10 to the negative 5. On the top, I'm going to sub in x times x. It would have been a divide by 0.5 minus x, but I've already made my simplifying assumption. Relative to my starting 0.5, I actually lose really little of it. So now what we're going to do here is we're going to multiply the 0.5 up. 1.8 e negative 5 times by 0.5 with the square root gives me now an x value of roughly 3.0 times 10 to the negative 3. Okay? So this is sort of mirrored of our lesson from yesterday, although on yesterday's lesson they were all acid calculations. Once you find x, go back and reread the question. What were they looking for? This question here was asking you, what is the pH? Where do I land on that ruler? We had already decided that was a base, so I'm expecting it's going to be something bigger than 7. This x here is actually the placeholder for the equilibrium amount of the hydroxide. So this is actually just hydroxide concentration. Again, it was quite a lot of work to actually get to hydroxide, but from this point here, you're ready to use that box summary again. You can go over, calculate H+. You can go Kw divided by the hydroxide to get to H+. And then you can do, let's say, negative log of this H+, and that would end up giving you pH. Or if you prefer, you can go, let's take the negative log of this one. By negative logging hydroxide, I end up getting POH. And then I can basically take pKw, which ends up as 14 minus. So pKw minus the POH gives you pH. It was a lot of work to actually get to hydroxide, but seeing as we practice a lot of these conversions in part 1, once you know the hydroxide, you can re-express it in terms of hydronium, POH, or pH. I'm just going to do this top way here. Remember, water always has this ability to self-ionize. If you now know the hydroxide is 3 times 10 to the 3, what's the corresponding H+? How much will water sort of break up? It always ensures that there's H+ around. 1 times 10 to the negative 14. Let's divide out the hydroxide concentration, which I expect to be higher. 1e negative 14 divided by 3e negative 3. This gives me roughly 3.3 times 10 to the negative 12. At first, both the hydroxide and the H+ used to be 10 to the negative 7. In having this base here, we now have 10 to the negative 3, about 1,000 times more hydroxide particles. We also now have about 10,000 times less H+ particles. But there we go, that's our concentration H+. We can then find the pH by taking the negative log of this number. I don't want to keep carrying around these huge negative powers. I just want to figure out on my pH ruler where do I end up landing. If you can, keep the whole number in your calculator. Negative log of this gives me a pH of 11.48. And remember, the significant digits for pH, POH, pKw are always after the decimal place. It's still important to write the 11, just like in scientific notation. It's important to have the 10 to the negative, but in terms of a precision, in terms of significant figures, the significant digits are after decimals. Sig figs are after decimals. Okay? And you do a mental check for yourself. Well, this was a weak base. I do expect the pH bigger than 7. There we go. Okay? So hopefully you see a lot of similarities with our Ka ice tables that we worked with yesterday, but we needed that one added step. I need to first calculate Kw over Ka on the table because they don't list for you Kb values. We still have to write out the assumption, and we'll go from there. Okay. So let's try out another question here. Just a slight little spin off of the problem. I want you to determine the Kb. So actually calculate the Kb value for a 0.20 molar salt solution with a pH of 11.31. Okay, so that's the setup. We have a salt solution. They start off giving you an initial concentration of 0.20, which is good. We notice that again we're in the basic range, so pH is 11.31. Not just saying this pH tells you acid or base, but knowing where I actually land on the ruler. This one here does tell you basic. We can actually figure out, okay, well, it's good to actually end up as a basic salt. How do we do this here? We're going to start off with some generic salt here. Let's say it's an AB type salt. As a salt, let's say it breaks up 100%, we're going to get A plus and B minus. Because this is actually in the basic solution, I would expect it's actually the anion that actually hydrolyzes. Usually if it's the cation that actually hydrolyzes, it actually becomes acidic. So let's just take this B minus. You can think of it as the conjugate base of a weak acid. The B minus is going to actually steal a proton from water and end up forming HB and OH minus. Right? That's the only way we're going to actually end up creating more hydroxide than a neutral solution. Again, this one here, first thing is the starting concentration is not all that high, and also the pH isn't upwards to the pH 13, pH 14, so that indicates to me it's a weak base. Another reason I know it's a weak base, if they actually ask you to determine the Kb value, if I'm going to have some numerical value of Kb, it has to be weak. It has to be in equilibrium. Because strong bases ionize 100%. If I did a product over reactant, a number divided by practically 0, they're just going to stay on the table very large. Okay, so what we're asked to do here is we're actually calculating what is the Kb constant. Let's set up our ice table. Just like before, my salt, right, it was 0.20. It's going to break out to become 0.20, 0.20. I don't care about the spectator ion here. It's just going to swim around in solution. It's not going to interfere. But the B minus is actually starting off at 0.20. The I row here is before any ionization. So I have no HB, no hydroxide at first, right? Aside from what water would have self-ionized anyways. I would have been ready to go minus X plus X plus X like we did normally. But this time they actually give you added information. If I take the solution, once the B minus has had a chance to actually steal the proton from water, it ends up generating enough hydroxide in this beaker that the hydroxide, the pH is actually 11.31. So they've actually given you the pH reading. Again, once they give you one of these numbers here, we can work around this diagram here to actually get, I can get the corresponding H+, I can get the corresponding POH, whichever way you want. For this time, because my ice table is going to track hydroxide concentration, what I'm going to want to do is I want to calculate for hydroxide. So let's go around the other side of the diagram here. To calculate POH, 14 minus this pH. I can go 14.00 if you like there. So 14 minus 11.31 gives me a POH of 2.69. Again, the significant digits are after the decimal place. How do we get back to just hydroxide? I need to undo the negative log, so I go anti-log, so it's 10 to the power of negative 2.69. And that gives you here anti-log negative 2.69 gives you 2.0 times 10 to the negative 3. Back when we had pH, POH, significant digits were after the decimal place. When you get it back into the regular old scientific notation, the significant digits are the base numbers. Okay. So some people do prefer just writing it like this. Oh, the hydroxide concentration is anti-log of negative 2.69 like that. If that confuses you, you can just sub in instead. Well, when I actually crunch through the numbers, that's actually 2.0 times 10 to the negative 3, 0.002. Okay? Because I'm given information about the equilibrium row, great, I can then find the change. Well, starting from no hydroxide, I would have gained 2.0 times 10 to the negative 3. The change line follows a mole ratio, so this one here also goes up, 2.0 times 10 to the negative 3. These ones here are going to equal because they're in a 1-to-1 ratio, and the other one is going to have dropped by 2.0 times 10 to the negative 3. Back in the earlier question, this is where we did the assumption. 0.2 minus so little actually breaks off is basically 0.2. Well, I don't need to make the assumption. The assumption was just to make the math easy. This math is already really easy. Let's go 0.2 minus 2e negative 3. This gives you a value of 0.198. So only assume when you have to. I'll actually demonstrate to you in the next question using a quadratic. The assumption is actually not that bad, but in this case here, we actually didn't need the assumption at all. We're interested in calculating for the Kb value. Kb, I would still write out the expression. So the acid form, Hb, times hydroxide all over B minus. If only I had those three numbers, I can just multiply the tops and divide the bottom, and I got it. And there we go. I actually have the numbers. Anytime you have this equilibrium row, you can just sub them directly into the Kb expression. So we're going to get on the top 2.0 times 10 to the negative 3, so 0.002, multiplied by the same number, 2.0 times 10 to the negative 3, all over the B minus. Even I had predicted the Kb is going to be very tiny. I predicted most of the 0.2 would stay here. 0.198 is practically 0.2. But yeah, there's a little bit of it that actually breaks off. To be really, really precise, I can say, oh, there's actually 0.198. Let's calculate this through here. 0.198. So 2e negative 3. I'm going to square that number divided by 0.198. Gives me roughly 2.0 times 10 to the negative 5. Okay, so I've done it. I was told I had this salt. I had predicted that it was the anion that actually hydrolyzed. The Kb for this salt here has to be 2.0 times 10 to the negative 5 for it to ionize enough to generate hydroxide so that the final solution has a pH of 11.31. Just for comparison's sake here, this Kb is an intensive value. It's specific to the chemical composition. Unfortunately, on the table, I'm only, again, I have acids on the left, bases on the right. I'm only quoted Ka values. Knowing that relationship from earlier, right? Kw is Ka times Kb for conjugate pairs of each other. Let's see if we can figure out what is the Ka conjugate acid and actually see if it matches anything on the table. So they didn't ask you to do this, but knowing the Kb value, we can actually recalculate the Ka. The Ka is going to be 1.0 times 10 to the negative 14, the Kw, divided by this Kb. 2.0 times 10 to the negative 5. So 1e negative 14, divide this answer, gives me roughly here 4.95. So let's go 5.0 times 10 to the negative 10. Again, no units. You can look on the Ka table. This one here tells you your acid ionization constant. This tells you your strength of acid. The Ka on the table goes from a strength of acid. So we have our weak acids, so strong acids, and then we have our weak acids. Starting off from our weak acid section, the Ka drops from 1 down to 1 times 10 to the negative 14, where towards the low end, my acid is having trouble going forwards. I want to see if there's anything that's close to 5.0 times 10 to the negative 10. The closest value that I see here, again, our table is not an exhaustive list, it doesn't show you everything, but the one that's really close to that 5 number here is maybe this 4.9 times 10 to the negative 10. That equation there, maybe I should write it up on the top. So maybe it's this, right? It could totally be wrong. Maybe it's just some rounding errors. 4.9 times 10 to the negative 10. And that equation is actually HCN equilibrium becoming H plus and CN minus. Again, be careful, the values on the tables are acid constants. That tells you how good my acid form, HCN, is actually good at coming forwards. We have been dealing with a salt of the base. The base is maybe CN minus. Earlier that we had talked about, oh, it's just some AB salt here, it ionized to get B minus. Now we have some support for the fact that this B minus is actually the cyanide ion, CN minus. Okay. Again, they didn't ask you to do that, but that's how it sort of links back to the table. Right? One last question here, just for practice. Right? I'm going to give you another salt. It's going to hydrolyze. Let's see if you can go through all the steps here. So, last question. I want you to calculate. Hopefully you're feeling this part here is very similar to yesterday's lesson, which it is, right? But we're just doing it more so on the base side. I want you to calculate the concentration of hydroxide in a 0.25 molar NaHC2O4 minus solution. Just like before, if they just ask you, calculate the pH, that doesn't decide acid or base. In this case here, they're actually asking, well, how much hydroxide in solution? If the hydroxide is high, sure, it's basic. If the hydroxide is actually a lower number, then it's going to be acidic, right? So just asking you to quote for me the hydroxide number doesn't specify acid or base. What's going to decide it for me is when you look at the compound, ask yourself, what is this? Is it an acid, a base, a salt? If it's an acid or base, is it a strong or weak acid? In this case here, you should be able to identify for me, well, this one here is a salt. This is back to our hydrolysis lesson. So we're going to take the salt here, sodium hydrogen oxalate. As an alkali salt, it rips up 100%, Na plus and HC2O4 minus. So if I had 0.25 molar of my salt, this is going to be completely gone. I would have 0.25 molar of the sodium, 0.25 molar of the hydrogen oxalate. Based on a hydrolysis style question here, we want to cancel any spectators. This one here is a group 1 salt. Group 1 salts are usually soluble, so these ones here are spectators. Once you get sodium in solution, they're just going to swim around. They're not actually going to interfere with water. Our spectator anions were conjugates of strong acids. This one is definitely not a conjugate of a strong acid. So we want to look for this one here on the table. This one here has an H, so potentially it could be an acid. It also has a negative charge, so potentially it could actually pick up a proton and actually be a base. Chemicals that have this ability here, remember we refer to these ones as amphiprotic. Right? So it could be acid or it could be base. It has to choose one or the other, right? The final solution, it can't be acid and base, right? It has to choose one. So what you need to do here is just a little bit of work from our hydrolysis lesson. Let's look on the table and let's find where we see this HC2O4. About midway down the table, acids on the left, bases on the right. The acid on the left here is HC2O4 minus. Again, on the table, everything's been simplified. As an acid, my ability to actually lose that proton is given by the Ka value directly on the table. The Ka is actually given as 6.4 times 10 to the negative 5. Okay. Fairly decent Ka. In general, it's a very tiny number, but it's a 10 to the negative 5. I also find this hydrogen oxalate ion fairly close to the top. Not in that strong acid section. We had said it's not a conjugate of a strong acid, but HC2O4 minus can pick up a proton also in the sort of weak base category and end up becoming H2C2O4. I'm going to quote the Ka for you here. The Ka for that is actually 5.9. Ka is 5.9 times 10 to the negative 2. Okay. Yes, in some sense, I do need to compare. Does it want to be acid more or compare more to be base more? I know its ability to be acid is 6.4 times 10 to the negative 5. Unfortunately, the table only lists for you Ka constants. This 5.9 number actually talks about how good my partner is in coming forwards. We still need to do a calculation. Well, if I am actually the base in this situation, the hydrogen oxalate, if I go, what's the Kb value? I would still need to go Kw divided by Ka. Just remember, it's the Ka of the equation I want to reverse. Even though the hydrogen oxalate itself has an acid ionization constant, if I actually divided by this one, I actually would have found the Kb of my oxalate ion. It's the equation I want to undo here. I want to take Kw divided by that Ka, 1.0 times 10 to the negative 14, divide out our 5.9 times 10 to the negative 2, and this gives me here 1e negative 14 divided by 5.9e negative 2. That gives me 1.7 times 10 to the negative 13. Right? So now we had the salt, right? It ionized. We got this ion that could potentially be acid or base, depending on what else is in solution. In this case here, looking at the numbers, how much does it want to be acid? 10 to the negative 5. How much does it want to be base? 10 to the negative 13. We can make this conclusion here. Since Ka is actually bigger than Kb, it wants to do the acid equation more. The overall solution will be acidic. So we could have actually done this problem yesterday here. This boils down to a Ka calculation. I'll leave this for you to solve it out and encourage you just to set up your ice table, see if you need to make an assumption, and then you can check your work with me. I'm also going to demonstrate to you, if I showed you the quadratic equation, it's a lot more math, but pretty much our assumption does a really good job of this. Right? So just pause the video here. Assuming that you've done that here, we can just check our work. Let's take this acid now. In the equation, it's simplified. Let me write out the whole equation. HC2O4 minus and water in an equilibrium. It ends up forming hydronium and then C2O4 minus. We had calculated the Ka constant is going to be 6.4 times 10 to the negative 5. we have an ice table, because this one here is a weak system. It's an equilibrium system. Because the Ka constant here is fairly tiny, very little is actually going to be tossed over. I had initially had 0.25. So 0.25, I always think of this sort of as a box. Being something that's weak, the constant is so tiny, not a lot of it's going to break over. The initial line here is before any ionization, so I had 0 and 0 to begin with. This time I'm not given any information about the ending, so we're going to go plus x. I can't drop any lower than 0. 0 plus x is x, 0 plus x is x. This one here is going to drop by x, but this is the part so little actually fractures over that we're going to pretend this 0.25 minus x is essentially 0.25. It's just important for you to just write the assumption. I know it makes the math easy. Assume this 0.25 minus x is basically 0.25. Again, I've been saying it sort of says this x here is unimportant, and yet we're going through this calculation to try to figure out what is the size of this x number. Anytime you have this equilibrium rule, you're ready to put it into the equilibrium expression. So we have Ka this time. Ka is given by the products, hydronium times your oxalate, divided by HC2O4 minus. The Ka value you can just read directly from the table. We calculated 6.4, we just read it there. 6.4 times 10 to the negative 5. This is going to equal to x times x. And then we had the HC2O4, it would have been 0.25 minus x. We would have needed to do a quadratic, but with the assumption, I'm just going to put 0.25 minus x. So we're going to just bring that term up, and then with the square root, let's figure out what x is. So 6.4 e negative 5 times 0.25 with the square root. The x is actually 4.0 times 10 to the negative 3. Okay. We can actually at this point here test the assumption. If the x value based on my assumption is actually 4.0 times 10 to the negative 3, 0.004, 0.25 minus this answer is practically 0.246. Well, yeah, that's pretty close to 0.25. And we're going to see something very similar. I'm going to solve it out with the quadratic formula. We'll practically get the same thing to justify that the assumption is very good. Now remember, even though it may have been a lot of math to actually get to this, go back and reread the question. This question, they were actually asking you for the hydroxide amount. Now, we had decided it was acidic, so that just means that water would self-ionize, only regenerate a little bit of base. The X that I end up finding is the equilibrium content of the H3O+. This one here is actually the concentration of H+. Remember, once you have one of the expressions, you can go around that box, you can calculate OH-, you can calculate pH, POH, you can do all that. This time they just want the OH-, so let's just do the one calculation over. The OH- would just be Kw divided by the H+. So it's going to be 1.0 times 10 to the negative 14 divided by this number here, 4.0 times 10 to the negative 3. And this gives me a hydroxide content. 1e negative 14 divided 4e negative 3 gives you a hydroxide amount. I don't know why I wrote this backwards here. OH- is 2.5 times 10 to the negative 12. And as expected, it's a very tiny number. The H+ was some 10 to the negative 3 molar, whereas the OH- is at 10 to the negative 12, about 9 orders of magnitude tinier. Okay. Again, just be careful. Them just asking you, find the pH or find the OH doesn't actually specify acid or base. You actually need to look at the chemical involved. Just for fun, I'm just going to demonstrate to you. Sometimes people are like, well, I can do the math. I can do quadratic, right? Why simplify it for us here? I'm going to show it to you with the quadratic formula, just this sort of last little math step here. It's going to be way harder in terms of the math, but we are going to end up with x as pretty much 4e negative 3, and therefore you can basically use the assumption from here on out. Okay. So just for comparison's sake here, if you wanted to use the quadratic formula, using the quad formula, so let me just rehash this one here. I have this 6.4 times 10 to the negative 5. We had an x squared on top. It was this bottom part that would have had the quadratic, 0.25 minus x. I would want to pull up this term here. This is totally just for fun. 6.4 times 10 to the negative 5. 0.25 minus x has to give you x squared. I'm going to distribute this really tiny number in. So 6.4 e negative 5 times 0.25 gives me 1.6 times 10 to the negative 5 minus 6.4 times 10 to the negative 5x. is equal to x squared. Usually you would push everything over to one side, but this time, since it's a quadratic, let's push everything over to the right hand side. So we're going to have 0 is equal to x squared. I'm going to add the 6.4, this number over. So let's add 6.4 times 10 to the negative 5x, and then let's subtract this 1.6 times 10 to the negative 5 over. These are all just scientific notation numbers. Remember, from your math classes, a is the number before the x squared, so a is 1. B in this case here is this 6.4 times 10 to the negative 5, and then c is actually going to be this entire constant, negative 1.6 times 10 to the negative 5. Now we look at our formula sheets here in your math classes. The quadratic basically says the x that solves it is actually negative b plus or minus a very scary term, b squared minus 4ac divided by 2a. So let's just plug through our numbers here. Let's take the negative of b, 6.4 times 10 to the negative 5. Let's do a plus or minus. We have the root of this same number, 6.4 times 10 to the negative 5, all squared, minus 4 times a is 1, times our c value, negative 1.6 times 10 to the negative 5, divided by 2 times a. Let's clean this up. Negative 6.4 times 10 to the negative 5 plus minus. I'm just going to type in what's underneath the square root here. 6.4e negative 5 with the square, minus 4 times 1 times negative 1.6e negative 5. Underneath the square root, this bottom part, make sure you're getting 6.4 times 10 to the negative 5. We take the square root of that number, and that gives me here 8.0 times 10 to the negative 3 divided by 2. At this point, you're ready to do the plus or minus. So if you take the plus root, again, the final answer may not be 1 positive, 1 negative, but at least depending on what this numerator ends up being, one takes the plus and the other takes the minus. So there's the plus side. The minus side is negative 6.4 times 10 to the negative 5. We're going to minus off that same 8.0 times 10 to the negative 3. You see it's a lot of math, a lot of work to actually get to this. So with the add root here, this one here gives me, I'll give you more decimal places, 3.97 times 10 to the negative 3. That's one answer. Or the other answer is negative 6.4e negative 5 minus 8e negative 3 divided by 2 gives you a negative 4.03 times 10 to the negative 3. Because this one here is an x, and x is actually the equilibrium concentration of my acid, it can't be negative, so we have to reject this solution. And therefore, if your x value is 3.97 times 10 to the negative 3, that practically is 4 times 10 to the negative 3. So just to show you, just for fun here, we had done it with the assumption. I had already tested the assumption. It's not a bad assumption, but even if you do all the quadratic formula here and you solve all that work, you end up running into basically x is going to be 4 times 10 to the negative 3 anyways. We just simplified the math quite a lot, and then we're able to get to our final answer. Okay, so keep practicing through those problems. Let me know if you have any issues. Thanks, guys.